Welcome to NASA Edge.
An inside and outside look at all things NASA.
Hey, we're here on the balcony of the Operations Services Building 2 at NASA Kennedy Space Center, and right behind me is the famous Vehicle Assembly Building.
And over Chris's left shoulder off the side of our set is a view of Space Launch Complex 41 over at Cape Canaveral, and that's where tonight in about an hour and a half we will have the launch of the MMS, the Magnetospheric Multiscale Mission.
Now the cool thing is that wide shot that they were seeing is actually the camera on top of the VAB with the long lens.
It's a great shot, and we'll see many more shots of the pad and video throughout the rest of the show. Now, this is not our first introduction to the MMS mission. NASA Edge has been following MMS for about the past 4 years, and we have done 5 shows. And over the next hour and a half, we will introduce you to some of the people that are associated with the MMS program throughout the show. But one thing that you might have noticed when we started is that Blair is not on this part of the set with us. He is actually in his own habitat or clean room.
His own world.
His own world here on the roof with us here. And Blair, tell us a little bit about your new clean room and the changes that we've made since your old habitat.
I'm sorry, Franklin. It was so comfortable and clean in here that I didn't hear what you were saying. I was busy just working on social media, getting ready for the show. I got to tell you, it's absolutely cool to finally take that next step. You know, I've done this in beta in different ways over the years, and now to have my first commercially and scientifically viable clean room to do research and social media virus-free, awesome. And as you can see, it's just brilliantly put together.
Blair, what are some of the modifications that you made since the beta version?
Well, it's clean. That would be the first thing. I mean, it's hermetically sealed almost and positively pressured. And plus, I've got electronics and gear in here that will help me do the research I need to do.
Tonight, you're going to actually be bringing us information through social media.
Correct.
And you're going to be providing the questions from our viewers. Tell us a little bit about that.
Well, it's interesting. I thought in honor of the work that's been done, I would just sort of manage all the social media that's coming in. So I got to tell you, it's going to be some good stuff here on the show tonight. I've got lots of things cooking right now, very cleanly though.
And welcome back to NASA Edge. We're here with Alex Young from NASA Goddard Space Flight Center. How you doing, Alex?
I'm doing great. How are you doing?
Not too bad. Hey, this is an exciting night for a launch, isn't it?
This is fantastic. I couldn't think of a better place to be and a cooler event to be witnessing tonight.
Now, it's kind of interesting because we're launching at night, but we're looking at the sun and that interaction between the sun and the Earth. And that's what your focus is in the Heliophysics division at NASA Goddard. And kind of give us the big picture. I mean, why do we study that sun-Earth relationship?
Well, the sun, it is literally the center of everything. Besides being the source of all of our heat, all of our light, it's constantly spraying out these gusts of particles we call the solar wind. Magnetic field is streaming out, and this fills the entire solar system. It makes this giant bubble around the solar system that we call the heliosphere. But that interacts with all of the planets, but it also interacts with the Earth, and it has a very, very powerful impact on us here on Earth. And so it's really critical that we understand that.
When we look at this MMS mission, how does that particular mission fit into the Heliophysics portfolio?
Well, you know, it's part of this greater fleet we have of 18 missions, even more individual spacecraft. But the cool thing about MMS is that it's serving as our laboratory up close. It's going to study something that there's no other place in the solar system, there's no other place in the universe that we could actually study. So it is a critical piece of this bigger heliophysics picture, and we are going to see some amazing results from it.
Take us to the process. I mean, how do you determine what would be the requirements or the science objectives for this mission?
Well, you know, it's based on not only theory. You know, this is something, this process that we're interested in called magnetic reconnection has been studied since the 40s. And then over the years, we've launched more and more missions that have given us pieces, glimpses of this process. You know, so we have gotten secondary information that's indicated to us that it does exist, but as we get more and more technology, we get sort of closer and closer, finer and finer,
right.
And what we're doing now is we're finally making the view close enough that we can see that scale. So it's a matter of having kind of improved the measurements over the years, and now we actually have the technology that allows us to see this really, really fine detail that we've never seen before.
Well, you know, Alex, there's a lot of questions out there that our fans want to ask you. And so we're going to go to Blair. Of course, he's in his clean room. Blair, we have our first question.
Let's go with at Scott Milkus from Twitter. He says, could MMS data be used to predict solar or space weather events in the future?
Well, that's a really good question. Unfortunately, the immediate answer is no.
Okay.
It's not going to actually allow us to predict solar weather, space weather as we call it. However, the engine for solar weather, the driver for solar weather and space weather is magnetic reconnection.
Okay.
So understanding this process is critical for us to eventually be able to do the prediction. Okay. So in that sense, it is really, really important part.
And now we're joined by Susan Pope, who's a program director for Space Science and Engineering Division at Southwest Research Institute.
That's correct.
How you doing?
I'm doing great.
So you pumped and jazzed?
I'm a little pumped. I'm pretty excited.
Now, when it comes to MMS, you work on the engineering side at Southwest Research Institute?
Yes, that's correct.
And what do you specifically work on the mission?
So I am the lead instrument suite systems engineer for MMS.
Okay.
And so my responsibility was to lead the development of the instruments. And we had instruments from all over the world.
How challenging is it to work with all those partners on a pretty complex mission such as MMS?
You know, it was challenging, and what I did to help out a lot was involve a lot of different people who I knew could specialize in certain things. I have a mechanical engineering background,
okay,
so I'm not going to be able to answer and make sure that the software and the electrical engineering and everything works the way it's supposed to work.
Right.
So I would just gather the people around me that I needed to be able to make everything work, and I had a great team. The lead systems engineers for each of the instruments were all very, very good,
okay,
and really helped pull everything together that needed to get pulled together.
Now, are you given a sort of, let's say, what they call a set of requirements from day one and what you're supposed to be doing?
Yeah,
for those flight instruments?
At the beginning of the project, you're given the science requirements.
Okay.
So really, as a systems engineer's job, you're making sure that those science requirements are flowed down to engineering requirements that an engineer can understand in order to build a circuit board, for example. So we take those requirements, flow them down to the instruments. The instruments then flow them down to their smaller components as part of the instruments.
So really, in reality, you have to sort of be like MacGyver to try to figure out, can I build an instrument that will meet those science requirements and fit in the spacecraft?
That's correct.
Right.
Yeah, there was a lot of that. The other thing about these instruments, there's 25 on each spacecraft. Most of the instruments have what we call a field of view, which is where the ions or electrons or whatever they're measuring actually come in.
Okay.
And they all have to be mounted around the perimeter of the octagonal spacecraft where they only see space, they don't see an antenna, for example. So we had to position some of them in an area where they were straddling the mag boom, for example.
Gotcha. Okay.
So the fields of view were on either side of mag boom. So it was definitely a challenge, and that was one of the things we did at the very beginning, was make sure that we had everything in the right spot, making sure everything was doing what it needed to do in that specific area.
Are you designing, one instrument at a time, or are you trying to design all 25 in conjunction with each other to try to fit that into the spacecraft?
So that's actually a very good question, because one of the things in systems engineering is not just, say, science requirements, but also interface requirements, because everything is built at the same time. It isn't like you build this thing and then build another thing to mount it on. So you do it all at the same time in order to get the job done and when it needs to get done. So.
And I think I see Blair in the clean room. He's working hard at social media, so I think we have a few questions. Blair, anything for Susan?
Well, yeah, certainly. I gotta. Sorry, there are bugs somehow in my clean room, which is a violation of.
It's definitely a violation of clean room.
We need to get version 3 out here.
My positive pressure devices are failing. But sorry, Susan. One question along the instrumentation side. One of our viewers wants to know. The spacecraft are identical, so how difficult is it to develop and build instruments that have to be identical? I know you build a lot of different ones that have to connect, but they're really wondering about replicating that all at the same time.
So we did have to do that, and that was one of the things we did struggle with. Each of the spacecraft has 4 dual ion spectrometers and 4 dual electron spectrometers. So that's 4 times 4, which I think is 16. I'm a little nervous.
Yeah, that's true. Yeah, that's true.
And so there were 16 of each of those on the full spacecraft, and they all really need to have the dimensions that are the same.
Right.
So what we did was we did that through tolerancing. Okay. So you bring a part to a machine shop and you do an analysis to make sure that the diameters are going to be close to the same.
Right.
So you put that on your drawings, you build your parts, you put it all together, and then we do what's called calibration. So we put the instruments in a vacuum chamber to simulate the vacuum. We shoot an ion and an electron, depending on what they're measuring. and then we can take measurements and see what each of the instruments sees. And so we really do understand the intricacies of each of the instruments, and we also know where each of the instruments is mounted.
Right.
So we try to make it so they measure and look exactly the same.
Dr. Pollock, you're going to be blinding me with science for about the next 10 or 11 minutes. Tell us a little bit about the science that's going to take place with MMS.
Well, MMS stands for Magnetospheric Multiscale. And it's called Magnetospheric Multiscale because we're studying things on multi-scales. We're studying magnetic reconnection, which happens in very, very localized places, but then can affect global systems like the surface of the sun and the Earth's space environment. So even though that reconnection occurs in a tiny location, it can affect the topology of a very, very large system, millions of times larger than the volume of space where reconnection actually occurs.
And this is in the magnetosphere where this takes place.
This happens in the magnetosphere. It happens on the surface of the sun and below the surface of the sun. It happens on other stars and in galaxies and in the vicinities of black holes.
So what is fast plasma?
Fast plasma, we call it fast plasma. It's not the plasma that's fast, it's the instrumentation that's fast. The magnetic reconnection happens in a tiny volume of space, and that volume is often moving very quickly at 50 kilometers per second or so, and it washes over the spacecraft, and we have very little time to make the measurements. So in order to make those measurements, we have to make instrumentation that's very fast. On each spacecraft, there are 4 dual electron spectrometers and 4 dual ion spectrometers. That makes 8 spectrometers for electrons and 8 spectrometers for ions on each spacecraft. And the reason we do that is because the spacecraft are spinning at only 3 revolutions per minute. But we have to make the 3-dimensional ion and electron distribution function measurements in 30 milliseconds. So we have to make that measurement 30 times in a second, looking in all directions. So we can't wait for spacecraft spin as traditional missions have done. So what we've done is proliferate many of these spectrometers around the perimeter so we can look in all directions at the same time.
Well, when you talk about magnetic reconnection, it implies that there was a disconnection. What's taking place and what causes the connection and reconnection?
Well, I've had a little bit of trouble with that terminology myself all these years. What's really happening is a magnetic disconnection. Magnetic field lines are breaking. As the interplanetary magnetic field lines impinge, for example, on the Earth's magnetic field, the interplanetary magnetic field lines break, the Earth's magnetic field lines break, and then the Earth and interplanetary field lines join each other so that those things that used to be strictly interplanetary are now partly interplanetary and partly Earth's magnetic field.
Now, what kind of impact does magnetic reconnection have on us here on Earth? Or is there anything that we can see?
The Northern Lights is the best example of things that we can see. If we have appropriate instrumentation to look at the sun, we can see solar flares. That's another thing that we can see that's visible. But the most obvious and the most commonly observed manifestation of reconnection on Earth is the aurora borealis and, of course, the southern lights in the southern hemisphere, the aurora australis.
Sounds great, Dr. Pollock. We'll go over to Blair. Blair, do you have any questions for Dr. Pollock?
I have a lot of questions, and they cover a range of some of the things that he has been talking about. So I'm just going to go through these the best I can, obviously one at a time. Lonnie Sass asks, does the moon have any effect on Earth's magnetic fields?
The moon has very little effect on the Earth's magnetic field. The magnetic field of the Earth actually penetrates right through the moon. The moon itself is not magnetized, so it really does not have strong effect on the Earth's magnetic field.
Would you say he answered that question efficiently and thoroughly?
It was to the point.
Okay, so I'm going to have to step it up and go with a more difficult question, a more complex one. So try this one. This is from Doug at Destin Doug. If plasma as a fourth state of matter only exists in superheated environments like the sun, how can it exist in the cold void of space?
Well, plasma doesn't only exist in the superheated environments like the sun. For example, there's a lot of plasma in our own ionosphere, just 80 or 100 kilometers above the surface of the Earth. And it's hot by the standards of our own human sensitivities. But for example, the plasma in the magnetosphere further out from Earth is on the order of 100,000 degrees or 1 million degrees in temperature. The plasma in the ionosphere directly above us is only a couple of thousand degrees. So you don't need extreme heat for plasma, but you need substantially more heat than you were used to experiencing here on the surface of the Earth.
Dr. Pollock, thank you for being on the show with us today. I know you had to hurry on over here, and I know you're looking forward to getting one of the best views here at the Kennedy Space Center of the launch from Cape Canaveral. So thanks again for being with us.
Well, thank you. It's my pleasure.
All right. Earlier this week when we got to the Kennedy Space Center, we had an opportunity to go over to the Cape, and Blair sat down with Paul Gross from ULA to talk about the partnership between NASA and ULA in getting MMS into orbit.
We're here at the Atlas Space Flight Operations Center at Cape Canaveral with Paul Gross, who's the ULA mission manager with MMS. Paul, you're a mission manager.
Yes.
I mean, that is the coolest title. I would love to have that title someday, but what do you do as the mission manager?
So my job really starts when we get something called interface requirements from the spacecraft folks through LSP, NASA's Launch Services Program, to ULA that say, okay, for my mission I need to have this sort of structural interface, this sort of electrical interface. I need this stuff in order to make my mission happen and get this ride into space successfully. And so we work on developing a solution, basically an overall technical solution to meet that list of requirements.
How difficult is it to match these spacecraft up with the launch vehicle?
Some of it's fairly straightforward. It's what we call a standard service. Almost every spacecraft may have some things that are real similar, and some of it is mission unique. And in this case, most of the mission unique stuff has to do with the fact that MMS is 4 spacecraft that are stacked one on top of another. Normally we might just have 1, sometimes 2, but 4 spacecraft of this size was really a first for the Atlas launch vehicle program.
Was that a surprise when you saw that on the proposal? Did you think, NASA's gone a little crazy putting 4 spacecraft together, or do you just expect any kind of challenge from them?
Well, in this case, they had done some thinking ahead and apparently looked at our payload planner's guide, because if you'll look at the spacecraft relative to the payload fairing, these things were designed to pretty much take up every available inch of space in that payload fairing. So there was some thought going into this on the spacecraft side as well.
So obviously as a mission manager, you're involved very early in the process. About how long are you involved with a normal NASA mission?
Several years. In this case, we actually had an extensive, what we call early integration phase. But normally the standard integration, we call it, kicks off 2 to 3 years ahead of time. So that's when I really get involved in developing that kickoff, where we bring all the technologies together and we meet all of our counterparts. NASA LSP has sort of a parallel team to ULA, and the spacecraft folks come and they tell us all about all of their spacecraft systems, and we start to realize, okay, we've got all these details to work out, and it takes years really to methodically work through all of that.
Yeah, I can barely plan my kids' birthday parties. I can't imagine the complexity that you guys face on that end. But I understand today you have a launch rehearsal.
Yeah, so what we're going to do today is the mission dress rehearsal, which really is a countdown practice. It's an abbreviated countdown because the one on launch day is 6 or 7 hours and can be quite extensive. So we bring together the 3-party team, in this case for MMS, ULA, NASA Launch Services Program, and the Goddard MMS project folks for the first time, where we're all sitting on console and everyone has their headsets on, and we need to learn how do we talk to each other, what are our call signs, and just general communication protocols. And they also throw some wild cards at us and see, okay, if we simulate this problem or that problem, how's the team going to react? And these things aren't just generic. They actually have a team that tries to ferret out what are the things these guys are still struggling with. Let's throw some curveballs at them and see how they do, so that if the same problem occurs on launch day, we're ready for it. And if everything goes really well, we might not have a whole lot of work to do to work on that stuff between now and launch day. But if there were some wrinkles and things, they'll make sure they iron it out. This person needs to understand they weren't supposed to talk to person A, they were supposed to talk to person B, You know, when they're using their headset, you got to push multiple buttons so people can hear you, that sort of thing.
Even those simple things are really important.
Right.
Yeah. One final question is, when does your role end? Because the space mission may go on for years and years. When can you relax, basically?
For the most part, it's at spacecraft separation. And in this case, for MMS, we have 4 of them, and they're 5 minutes apart. So it's really when that last one goes and separates from the launch vehicle, that's when everyone claps and does their sigh of relief. The launch vehicle still does a little bit after that. The Centaur upper stage will make some maneuvers so it doesn't crash into the spacecraft later on, because we don't want that to happen.
Of course.
And then afterwards, we do have some post-flight data reviews and things like that. So I'll probably really wrap things up and start to forget everything I ever knew about MMS about 3 months after launch.
Meanwhile, the scientists will be doing cheers with the data they're getting back. You're
right.
done.
They've had to kind of rely on us for a long time, but once separation occurs, they go into their mission mode, which will take them for years forward to do all the science mission on MMS.
I'm joined on the set right now by Mr. Troy Cline, who is the education and outreach lead for the MMS program. Troy, welcome back to the show.
Thank you very much, Franklin.
Troy, we've been talking about MMS for quite a few years now, and every time we meet up, you're doing some great public outreach. What exactly are you doing with MMS and outreach here at KSC this week?
This has been an incredible 3 days of full activity with about 25 to 30 students and teachers who've come to the center from 4 different states. We have people from Texas, Eubanks, Texas, which is a great call out to that school, an incredible school district. We also have students here from the second smallest school in West Virginia, from Paw Paw, West Virginia, and they're actually responsible for something I'll tell you a little bit more about.
Okay.
We also have students here who have been working with us from Pennsylvania and a couple other states, so we're really excited to have them all here right now. New Jersey as well.
Talk a little bit about the activities that you have going on.
One of the really awesome features that we have is a planetarium portable dome that's run by our co-lead for the MMS education program, which is Pat Reif, and she's been running this the entire time for 2 days in a row with I must be a couple thousand people that came through. And what's really exciting about that is the Grammy Award official artist, Lawrence Gartell, is actually here and created artwork just for us to place on the dome and to make a connection between science and art. And then also we have 25 students here, all in a sea of red shirts, and they are all at the booth and the table, and they're doing countless activities with magnetism, stomp rockets, which is a lot of fun to make. And last but not least, we have a gentleman who created 4 spacecraft observatories of MMS out of cardstock paper that are the most detailed cardstock models I think I've ever seen, and they're on display. And we also have Lego models that were designed by our students from the Mars Area Robotics team in West Virginia University, and you can download those models in all the directions as well online.
Speaking of West Virginia, you were telling me about a model or something that the students did there.
That is the actual, they built 2 models for us, and that actually morphed into a bigger project by the school in West Virginia, in Paw Paw. They actually built a life-size replica of the spacecraft, one of the observatories, out of balsa wood and actually real solar panels, right down to what looks like mylar right on the top and the covering. And it was so good that we invited them to bring it to Goddard Space Flight Center, where it was on display for a full month. And after that, this model will be traveling to the capital of West Virginia and be on permanent display, hanging in the main atrium and lobby of one of their just world-renowned museums there in the city.
Did you send your flatbed to go get it?
Actually, they had one. They had a NASA flatbed truck, and this spacecraft divides into 2 pieces right down the center. And so they pulled it apart, and we helped them carry it all in with several people there at Goddard. It took a little bit of work, but we were able to do it.
Earlier this year, I went to the Consumer Electronics Show, and Oculus Rift was very, very big there. And I understand that you all are doing something with Oculus Rift with regards to MMS.
We are so excited about Oculus Rift. It's a headset of virtual reality goggles that you can place on your head, and you also put some earphones on. And what happens is you start seeing everything in this virtual set. And so I've been working with this incredible web guru and technology expert, Brian Stevenson, at Goddard Space Flight Center from that area. So we worked with some of the people at Goddard, and we were able to bring the actual CAD drawing and what he needed to pull into Oculus Rift. And when we sat down and had a demonstration of what he had created, it feels like you are in space with the satellite moving right below you at 3 RPM and the Earth and the sun in the background. It's unbelievably realistic.
Sounds real good. Troy, thank you very much for being on the show. Right now we're going to go to the pad and pick up the commentary by NASA's George Diller.
25.
Status check.
Go Atlas.
Go Centaur.
Go MMS.
T-minus 10, 9, 8, 7, 6, 5. Go for main engine start. 3, 2, 1, 0. And liftoff of the Atlas V with MMS, using magnetic reconnection to fill in pieces of the puzzle of space weather.
These are some awesome pictures and video that are being sent back from, this is actually the aft-facing cam on the Centaur, showing the rockets actually firing right now.
It's a great shot, isn't it? I mean, what a super launch.
Super launch, went off on time, no problems.
I tell you what, we have to give props to NASA, to the launch services team, to ULA with the launch vehicle, and to the MMS science team, engineering team. What a great mission. They've been working on this for many years, and to see this launch tonight, now they're ready for the science.
And for more on the MMS mission, make sure you just head on over to the NASA portal at NASA.gov and look up MMS, and you can follow along with the mission and see what happens when the data comes back and see how the science works its way out.
Okay, we're going to sign off here from the Operations Services Building 2 at NASA Kennedy Space Center. Our live coverage of the MMS launch is complete, and let the science begin.
Absolutely. You're watching NASA Edge.
An inside and outside look, Blair?
Yeah, at all things NASA. I'm sorry, I blew the ending, but I'm in a clean room, so it's difficult.
All right.
All right.
Have a great night, everyone.